This is our work, titled Towards Uncertainty Unification, a case study for preference learning. Preference learning, as the task of learning a reward function from a set of items with known preference relationship, has become increasingly popular in robotics. For example, imagine a robot inferring Alice's, a human user, ideal trajectory for passing a cup of coffee above a table using preference learning. Suppose two possible trajectories, x1 and x2, are sampled. The robot asks the human to choose the preferred one. However, x1 poses a risk of spilling coffee on the keyboard, while x2 passes over headphones. Both objects are valuable to Alice, so she responds that she weakly prefers x2 with hesitation, reflecting her uncertainty in the decision. After collecting n human responses from n trajectory pairs, traditional uncertainty-averse models use only the preference answer, x1 or x2, ignoring human uncertainty. In contrast, we propose an uncertainty-unified model that incorporates both preference and uncertainty. Here, we define uncertainty unification as integrating human uncertainty into a robot's uncertainty-aware model, ensuring that both uncertainties influence learning and decision-making. We argue that uncertainty-averse models may yield suboptimal trajectories, such as passing over headphones. Our model, however, leads to a more desirable path. In this work, we introduce Uncertainty Unified Preference Learning, UUPL, using Gaussian processes, GPs, as our base model due to their well-defined variance, making them a natural fit for encoding robot uncertainty. Our key algorithmic contribution is integrating human preference uncertainty into the GP framework for preference learning tasks. Now we sketch our methodology. For a more detailed explanation, please refer to our paper. Consider a robot learning a human's thermal comfort function by asking preference comparisons. Instead of simply choosing between 18 Celsius and 20 Celsius, the human also specifies their uncertainty. Here, the human is very confident 20 Celsius is better than 18 Celsius based on their hidden reward function. First, we realize that different people have different definitions of uncertain and confident. To address this, we introduce an uncertainty calibration process to align uncertainty representations across diverse users, ensuring consistency and reliability in the model performance. Specifically, we collect user responses for a designed calibration function and computing quantiles, yielding uncertainty factors U1 to U4. For the human preference uncertainty model, we apply a probit model with Gaussian CDF. The calibrated uncertainty factors U1 to U4 define different sigmas in the CDF, as shown in the left figure of purple box. With such model, we are able to scale the Laplace posterior means for GP. In our case, the human is highly confident that 20 Celsius is better than 18 Celsius, so we use U1 as the CDF sigma. This creates the strongest separation between posterior means, visualized as the green line in the purple box. In terms of the GP variance, we implement an uncertainty-weighted GMM to unify human uncertainty with the GP posterior variance. The GMM weights represent the confidence extent. For a temperature point, higher user confidence results in a higher GMM weight. Additionally, the more frequently a data point appears, the higher GMM weight it gets. In this way, the GMM is used to weight and scale the posterior GP variance to integrate humans' uncertainty levels into the robot uncertainty representation. The left figure is the GMM for the example comparison, which results in a decreased variance at 18 and 20 Celsius, shown as the pink bar on the right figure. Combining these two results, we are able to get an uncertainty-unified GP, which provides more accurate posterior mean and interpretable variance, benefit from the three modules introduced previously. Next, we design three simulation experiments to test UUPL. The first one focuses on learning a user's thermal comfort function. The second one focuses on a tabletop scenario, where the 2D features are the XY coordinate on the tabletop. A higher reward value indicates a higher importance to the human user. The third one focuses on a driving scenario, where the users have to decide on the trajectory, given that the agent car is switching lane. Complex 4D features are extracted from every trajectory, which are the distance to the front car, speed, heading angle, and distance to the closest lane center. We compared our UUPL with three other methods, and UUPL consistently outperformed them in accuracy, efficiency, and stability. For detailed analysis, please refer to our paper. Beyond simulations, we conduct 2 real-world user studies with 8 participants. The first experiment involves a Canova Gen 3 robot performing the tabletop importance task. The robot starts at the blue star with a cup of coffee and navigates the table to reach the red star, while avoiding passing over important objects. The second experiment involves a Stretch 2 robot performing an apple pick-and-place task. It starts at the blue star, moves through a row of plants to pick up an apple at the yellow star, then bypasses a rack to reach the red star, where it places the apple on a plate. We test 3 methods with different uncertainty operations. The first one is the uncertainty averse model that doesn't consider user uncertainty. The second one considers uncertainty, but doesn't contain the calibration process. The last one is our full method with calibrated uncertainty. This is a demo setup for the first experiment. The tabletop contains many objects, including electronics, snacks, and toys. The user sits in front of a computer, interacting with the interface shown below. At each iteration, a red point and a blue point are sampled, and the user needs to select both preference and the uncertainty level. In this case, the user prefers controller than headphones, followed by the keyboard, cashews, and glasses case. For each method, we collect 20 preference pairs, and the learned reward functions are visualized below, where a brighter color indicates a higher importance. The final trajectories are shown as the red lines. Overlaying those images, we can see that the baseline trajectory passes over the headphones and glasses case, and the uncalibrated uncertainty model learns a similar trajectory. Conversely, our method learns the best trajectory by avoiding all important objects. The videos are shown below. It's worth noting that the robot's motion velocity is scaled with the GP variance, representing the trajectory uncertainty. This is another example of the tabletop importance task, featuring more objects and different user preferences. Similarly, the learned results of 3 methods are demonstrated below. As seen in these overlaid images, the baseline trajectory passes over the headphones, and the uncalibrated uncertainty model also generates suboptimal trajectory. In contrast, UUPL finds the optimal route, successfully avoiding all objects. The videos are shown below. Now we introduce the Apple Pick and Place experiment. The interface is shown above. For each trajectory, a red color indicates a higher speed, while a blue color represents a slower speed. One user prefers the robot to put the apple on the table as quickly as possible. The baseline method produces a long, slow trajectory, while the uncalibrated uncertainty model improves the path by increasing speed and moving closer to the rack. By comparison, with calibrated uncertainty, UUPL achieves the most efficient trajectory, optimizing both the travel path and velocity. Here we provide the corresponding videos. With calibrated uncertainty, UUPL accurately captures user preferences, completing the task quickly. In contrast, both the uncalibrated uncertainty and no uncertainty models result in significantly longer task completion times. Thank you for watching.